presentation, I'm going to show you our virtualization infrastructure for doing dynamic core library update. So the first thing that I should talk about to set a bit the context is about dynamic software update. So a dynamic software update is a software update that happens at runtime. So actually, the thing is that we are going to deploy new features to our programs at runtime, trying to minimize the downtime of our programs and the warm-up time. So that is to not restart the program every time that we have to deploy a new change. Yeah. So if we think about this use case is a perfect fit for reflection. So reflection is the ability of a program to introspect itself and to change its own behavior and its own state at runtime. So, for example, I have some examples of reflection. If we have a cat that is named Lutz, we can, using reflection, ask the class of the cat and get the class object of that object. And we can ask the name of the class and what are the instance variables. We can also change the behavior of the cat by adding new methods or changing the methods that are there. Yeah? So we can think about a dynamic software update system that uses reflection like this to deploy new changes to a system. But the thing is that reflection is not enough. So let's see why I see that. If we imagine that we want to deploy a refactor, we want to do a refactor in our core library of our language, and we want to, for example, we have an array class that defines an iteration method that is called do, for example, it's a for each method, and we want to move that do method to the superclass, yeah, to make all our objects iterable. So that's a really simple refactor. We just need to push up, or pull up, depending, the method, yeah. So doing that by reflection could look like this also. It is a fairly simple code that will remove the do method from the array class and will install a new do method in the object class. Yeah. So far, so easy. But how many of you think that this will work? Okay, nobody. So actually, the thing is that this does not work because there is a moment in the program execution where there's no do method, so there's no way anymore to iterate arrays. Yeah. So if our compile method needs to iterate arrays, then we are screwed up. And actually, what will happen if we try this in Pharo, the language that we use in the lab, what will happen is that compile will throw an exception because the do method is not there, and then handling the exception will probably raise another exception because of the same, and so on, creating an infinite regression, which we call a meta regression because it comes from the meta level of the language. So we gathered some experience applying some changes at runtime in Pharo. There are some handcraft solutions that we apply to solve this problem. One of these solutions is to sort the changes. So we can, for example, to make the example that I showed before work, we can just switch the order in which the two changes are done. So if we just add the do method and then we remove the old method from the array class, this change will work and our system will continue to run. Another solution, when changes are much more complex and we cannot use just sorting, is staging. So by using staging, we have to split our big change in smaller chunks, and we will try to execute these chunks in different steps, so we can apply all of them. Now, more complex changes than this one, this is a really toy example, are much more complex to apply, and we thought that we could do better. So first, we identified which are the challenges of doing dynamic update of the core of the language. First, we identified that there are circular dependencies between the update system and the updated element. Yeah. So when that happens, for example, we have our update script of before that is updating something that is used by himself, we may end up with a circular regression, an infinite regression. Then some changes are depend on the order. So we need to sort them or to apply them in a specific order because they require side effects. And finally, sometimes we find language restrictions, like, for example, if we want to change a class or an object that is tightly related with the virtual machine, we need to tell the virtual machine, hey, this is the new object that I updated. Please update yourself and update that reference. So given these challenges, the question that we ask ourselves is, what is the infrastructure that we need to update core libraries at runtime? So for this, we propose what we call a language virtualization infrastructure that we name SPEL. And I'm going to now dig a bit on this and a little dynamic software update system that we built and how we solve the challenges that I stated before. So first, in our virtualization infrastructure, the first thing that we have to know is that the application that we are running will run inside a kind of sandbox, and this sandbox is what we will call the virtualized application. So this is our normal application, and it is the guy that we want to update. Yeah? So far, so easy. Next to it, what we will put is another application. So both applications are written in the same language, actually. So in this case, it will be Faro. And we want, we will put in that guy that we call the hypervisor, the update system. Yeah? So the update system will reside in an external application and will interact with this virtualized application through what we call an object space. So let's see how we can install a dynamic an update system on top of this infrastructure. This is actually the code from the experiments we run. On one side, in the virtualized application, we have a web server that has an update point. It declares an update point that is a point in the execution where it is safe to update the application. And in the hypervisor, we will have the same code as before, but it will just not access directly the classes from the system where it is, but it will actually access the classes from the virtualized application. Yeah? So it will try to fetch the classes from the virtualized application and update them. So this the dynamic update system that we build is called Chester, and and this Chester will work like this. So first, if we think that we have our web server application here on the right, we will run this web server application until we find an update point, the update point that we declared before. And when we find an update point, if there are updates available, the execution of the virtualized application will be suspended, and we will give the priority to run to the hypervisor. This hypervisor will execute the updater that will apply the update, that will deploy the update in the virtualized application, and when that finishes, the execution will be resumed. So this really simple idea of going out, executing the update, and then coming back will give us atomic changes. These atomic changes, so in the virtualized application, we are applying all the changes at the same time, and for his point of view, it will be transparent. So with these atomic changes, we will get rid of the order dependability. We don't care anymore in which order the changes are applied, because for the virtualized application, it is all in one step. The next thing is the hypervisor. So one of the properties of this hypervisor is that it has its own copies of the core libraries. So each of the hypervisor and the virtualized runtime will have their own core libraries. And this will give us runtime independence. So the SPL hypervisor runtime will be independent from the virtualized application runtime, and then we don't have any more circular dependencies between the update system and the update system and the updated element. So then the last part of the puzzle is the object space object. So I said that our update system will talk to an object space object. This object space object is a first-class runtime. It's an object that will represent a runtime system, and it will provide us with operations to modify, to manipulate this virtualized application by, for example, modifying the language, creating classes, creating methods. It will also give us operations to modify objects in there through mirrors, in this case. It will also provide us with operations to manipulate the execution, like the stack or the processes. And it will also provide us with the possibility of reconfiguring the virtual machine and set those special objects that I said before. So the nice thing is that this object space will give us unrestricted access to the virtualized application, and it is from the outside. So we don't need actually support to modify the system from itself anymore. And actually, if we don't want to change, for example, the virtualized application to have to change the virtual machine, we don't need to, because it is actually done from the outside. So we run several benchmarks, the game suite benchmarks, on this infrastructure to see what is the overhead of having our virtualization infrastructure on an application. And actually, we saw that the overhead is not so visible. So actually, there are little differences between the normal application and the application in a virtualized environment. And these differences, we can argue that they come from noise in the environment. Then another evaluation that we did on this work is to execute, to see what is the overhead of doing a real update on a running application. So we run our web server from before, and while having a web application running, we applied an update in there, in the second 30. This update was actually a real bug fix from the Faro community. So we applied that bug fix in the second 30, and we saw that actually the overhead of applying that update in our virtualization infrastructure can be comparable to a garbage collection post. In this case, to a full garbage collection post. Of course, this may change depending on the size of the change. The bigger the change, the more time it will take to execute the update. But there is still work to be done on that side. So, as a conclusion, I'm a bit early, so I presented how our virtualization infrastructure provides us with atomic, non-circular, and unrestricted changes to update dynamically the core parts of the language with a negligible performance overhead. So, thank you very much.